In which part of the tube is the pressure greater, the wide part or the narrow part? The answer might surprise you. The pressure is greater in the wide part of the tube. We previously learned that a fluid travels faster in the narrow part of the tube. The fluid flow equation is A1 times V1 equals A2 times V2. Think of it this way. If the pressure were not greater in the wide part of the tube, then the fluid would not speed up as it moves from the wide to the narrow part of the tube. With less pressure in the narrow part of the tube, the velocity of the fluid can increase. This apparatus is called a Venturi tube. The fact that pressure is lower in the narrow portion has some interesting applications. In this atomizer, pushing air from the left creates a lower pressure in the center. Because the pressure on the surface of the fluid is greater than the pressure in the Venturi tube, fluid flows up the vertical tube. The fluid sucked into the narrow part of the Venturi tube is then blown out to the right. You may have heard that a prairie dog's front door is prominently displayed in a mound of dirt, but that he has a back door hidden some distance away for escape, in case a predator starts digging at the front door. Physics can suggest another function of this burrow design. As this sketch shows, the mound causes breezes to move faster over the door in the mound than over the back door. The resulting drop in air pressure over the mound pulls air through the burrow and ventilates it. This would also serve to move any prairie dog scent to the front door and away from the secret escape opening. In the 18th century, Daniel Bernoulli formalized the relationship between the pressure, velocity, density, and height change in fluid flowing through a pipe. We make the assumption that the fluid flow is non-viscous, steady, and incompressible. Bernoulli's equation is just this: the sum of the pressure plus 1/2 the density times the velocity of the fluid squared, plus the density times gravity times the height of the pipe above a reference point, is the same for any 2 points in the tube. In the pipe, the pressure, density, velocity, and vertical distance from a starting point are all related. Since the sum making up each side of Bernoulli's equation is always the same, regardless of the position in the tube, it must be equal to a constant. In our previous discussion of hydrostatic pressure, we concluded that the pressure at a depth, h, below the surface of the water is equal to the pressure on the surface of the water plus the density times the acceleration of gravity times the depth h. It is interesting that Bernoulli's equation expresses the same relation. If we take the velocity of the fluid to be 0, then Bernoulli's equation becomes the same equation that we use to find the pressure at any depth in a fluid. Let's derive this from Bernoulli's equation. If the fluid is not moving, then V sub 1 and V sub 2 are equal to 0. The equation can be rearranged as shown. Finally, simplify this to the pressure equation. Bernoulli's equation looks complicated. In the next few frames, we derive the equation from basic assumptions. Follow this derivation carefully, and the whole thing will make more sense. You'll recognize the bent pipe from our discussion of fluid flow. We're watching a slug of fluid move from the narrow end toward the wide end. At the narrow end, work is done on the slug as fluid pushes the slug to the right. The work done at the narrow end, W sub 1, is the force F sub 1 times the distance d sub 1 that the slug moves. Subscript 1 refers to the narrow end. From the definition of pressure, we know that force F sub 1 is equal to pressure P sub 1 times the area A sub 1 of the narrow end. Therefore, work is the pressure times the area times the distance. And, last, since the area times the distance equals the volume on the left, the work equals the pressure times the volume. At the wide end, the fluid to the right of the slug is exerting a leftward force on the slug. In this case, the work equals the negative value of the force times the distance moved, because the force is opposite to the displacement. The subscript 2 here refers to the wide end. The work done at the wide end can be related to the pressure and the volume as they were at the narrow end. The work done to move the slug through the narrow end of the pipe is the pressure times the volume there. And the work done by the slug pushing the fluid in the narrow end is negative pressure times volume there. The difference in these two amounts of work is the net amount of work. Because of fluid continuity, the volumes V sub 1 and V sub 2 must be equal to the same volume V. Let's pause a moment and then clean up a bit before going ahead. The work done on the slug equals the change in kinetic energy plus the change in potential energy. When the slug moves, its gravitational potential energy changes. Note that the mass of the fluid elements in volume V sub 1 and volume V sub 2 are the same, because these two volumes are equal and the density is uniform. The change in gravitational potential energy is the mass m of this fluid times the acceleration of gravity times the difference in height. The change in kinetic energy results from the difference in the speed of the fluid elements on the narrow and wide ends. Combine the equations for gravitational work, kinetic work, and net work. Now, divide through by the volume and then, using the fact that mass per volume is the density, substitute density for mass over volume. Next, regroup the equation so that all the 1's are on the left and all the 2's are on the right. We have derived Bernoulli's equation. Let's calculate how fast the water squirts from a hole punched in the side of a paper cup or other container of water. We make two simplifying assumptions. 1. The velocity at which the top surface drops approaches 0 because the diameter of the top is so large. 2. Since the top surface and the hole are open to the atmosphere, both are at atmospheric pressure. Follow the solution carefully. Notice that the density, ρ, and gravity, g, are the same at the top and at the hole. The final equation is called Torricelli's theorem. Torricelli came up with this theorem before Bernoulli developed his equation. Torricelli also used the concept of conservation of energy. He stated that the change in gravitational potential energy equals the change in kinetic energy. Let's check this. Set the gravitational potential energy of an object at a height, h, equal to the kinetic energy of the object after it falls a distance, h. If there is no change in height in Bernoulli's pipe, then the height factor can be left out. This gives us an equation with just pressure, density, and velocity. Suppose that the pressure at the wide end of an air conditioning duct is close to atmospheric pressure, 1.013 times 10 to the 5th pascals, and the air is leaving the wide end at 1.000 meters per second. If the velocity of the air in the narrow tube is 20.000 meters per second, what is the pressure at the narrow end of the tube? The density of air is 1.290 kilograms per meter cubed. Correct. If the difference in pressure is 100 pascals, what is it in pounds per square foot? Try again. Correct. An airplane wing has a curved upper surface and a flat lower surface when seen in cross-section. We have drawn streamlines along the wing and particles moving along them. A given pair of particles separate, and then they end up together again. The point here is that the top particle travels faster than the lower molecule. Let's put in some numbers for an airplane. It is a light plane. The chord of the wing is 1.000 meters, and the plane travels exactly 100 miles per hour. How fast does it go in meters per second? Solve this before moving on. Did you get it? This is the speed of the air under the wing. How fast does the air go over the wing? Let's assume the top is longer than the bottom with a ratio of 28 to 26.
Correct.
Now, use Bernoulli's equation to find the difference in pressure between the top and the bottom of the wing. You'll be working in pascals. The air was moving at 48.13 meters per second over the top, 44.69 meters per second over the bottom, and the bottom of the wing is 1.000 meters long. When you're done, convert your answer to pounds per square foot. Use 1.29 kilogram per meters cubed for the density of air.
Try again. Try again. Correct.
This number doesn't really deserve 4 significant figures because our main assumption was incorrect. We assumed that the airflow around the wing to be laminar. In reality, only a portion of the airflow is laminar. A great deal of the air passing over the wing is turbulent and not parallel. Also, the picture shows the bottom of the wing parallel to the oncoming air. Often, a wing has a positive angle of attack. Despite these simplifying assumptions, our answer of 14 pounds of lift for every square foot of wing is reasonably close to reality. Show a ping pong ball on top of a straw. The ball stays near the end of the straw. This is because if the ball drifts to the edge of the upward stream of air, the air in the center of the stream will move faster than the air on the side of the ball out of the stream. The faster air will have less pressure and the ball will be pushed back over the center of the straw.